Hey, this is Net Force 3. You're going to need your kinematics equations. There they are, just in case you forgot, but you should have them in your notes and have them handy. I think when I write them, I usually don't include, this has delta t squared, and that's supposed to be squared, so sorry if that was confusing at all. But you have them in your notes, and I think I put the, you have access to the kinematics equations notes also. Okay, so let's see how this works. A race car has a mass of 710 kilograms. It starts from rest and travels 40 meters in 3 seconds. 40 meters, that's a delta x. 3 seconds, that's a time. The units will always help you figure out what's what. The car is uniformly accelerated during the entire time. That just means we can assume that it's constant acceleration, which means that I can use those. How big is the net force acting on the car? Okay, so there's two different things here. Here's like the unbalanced force side of things, and here's the acceleration side of things. So over here, for the unbalanced force, if it's accelerating this way, I know that I've got a force of gravity of 7,100 newtons, force of gravity in the car from the entire Earth. There's a support force on the car from the ground, which would also be 7,100 newtons, because the car's not moving this way. That's balanced. And then there's this force of, we could call that traction, whatever you want to call it, on the car from the road. So this is the unbalanced force. And I don't have any way of finding it right here, right now, but I do know that unbalanced force, which is just this, that this is mass times acceleration is equal to the traction force. So if I want to know what that traction force is, I know the mass, and if I can find the acceleration, then we're good. And also, we missed this, starts from rest. That means that the VI is 0. So I'm going to write down my variables. I know acceleration, VI, VF, delta x, and t. So do I know the acceleration? No, but I'd like to, because that's what I need to multiply by the mass to find that. Do I know VI? Yep. Do I know VF? Nope. Do I know delta x? Yep. Do I know time? Mm-hmm. Okay, so what's the kinematics equation that relates those things? Why not this one? Because I don't know what this is, but that's not what I'm looking for either. I'm looking for acceleration. So that is the delta x equals 1/2 at squared plus VIT. You need to write down this equation that you're going to use before you plug stuff in. So delta x is 40, 1/2 a t squared is 9, plus VI is 0, so it's going to knock that term out. So I get 40 is equal to 9 halves, or 4.5 a. So a is 40 divided by 4.5, which is about 8.9 meters per second squared. So I can bring that over here. And that times 710, mass times acceleration, is about, I'm going to round to the nearest 100 newtons. It's about 6,300 newtons. That is how you do this kind of problem. Here's another one. Suppose that a 1,000 kilogram car is traveling at 25 meters per second. Its brakes can apply a force of 5,000 newtons. So that's like a braking force. What is the minimum distance required for the car to stop? Okay, so let's see what we have. Here's the unbalanced force side, and here's the like kinematics side. Over here, I need a force diagram. Multiply that mass by 10 there. Sorry, I'm getting lazy here. Force of gravity on the car from the entire Earth. This is the normal force on the car from the road. And let's say the car is going this way, then just like in broom ball, when you have to tap on the ball the other way, the braking force is going to be this way. The car is going this way, but the braking force would be the opposite to slow it down. Force of brakes on the car from the brakes. And that is 5,000 newtons. All right. So that means that the unbalanced force here, those would be equal and canceling each other out. The unbalanced force is just that braking force. And notice that that's like going this, the car's going this way, and the unbalanced force is like in the losing direction, like if the motion is this way. So you could say this, and then mass times acceleration. I've got a mass of 1,000 times acceleration is equal to negative 5,000. Now, if you're thinking to yourself, okay, I pretty much got all that, that makes sense, but I don't think I would have thought to put that negative sign in there. That's okay. You can catch that mistake over here. It's not necessarily a mistake, but you do have to pay attention to directions here. So let's write out our variables here. Excuse me. What's the acceleration? 5. Now let's pretend we didn't get the negative sign here so we can talk about how to deal with that. 25 meters per second is how fast we're going the start. If we want the car to stop, VF's got to be 0, right? And delta x, that's the stopping distance that we're interested in. And I don't know how long it takes, and I don't care either. That's not what I'm looking for. We want the distance for stopping, not the time. Okay, so what relates these things? That is the VF squared equals VI squared plus 2A delta x. And then when you plug stuff in, look at what happens here. You get 0 is equal to 25 squared plus 2 times the acceleration. Let's say we just thought that was 5 times delta x. So if you move this to the other side and then divide, you're going to get that the stopping distance is negative. You're like, what? That doesn't make any sense. So that is what is going to alert you to, oh, wait a minute. If the car is going forward at 25 meters per second and we want it to stop, the change in velocity must be negative, right? You're going to have to subtract 5 over time. Keep subtracting 5s from this. So somewhere along the line, you got to try to catch that, and that's going to be 62.5 meters. Worst case scenario is if you go through a whole problem, if it's like, on a test or something like that, and you can't figure out what went wrong, then just get rid of it. If there's a negative sign on something that you know can't be negative, then just get rid of it and hope that hope you get away with it. A 65-kilogram person dives into the water from the 10-meter platform. What's her speed as she enters the water? So when she's just free-falling toward the water, we've only got force of gravity on the diver from the entire Earth, no other forces, and that's 650 newtons, right? What's her speed as she enters the water? So I would need to know here, we didn't actually need that force diagram because I know in free fall the acceleration is -10, and VI, she's starting from rest. Her final speed as she enters the water, I want to know that there. Delta, I'm going to call it delta Y because it's a free fall problem and she's going up and down. If you call it X, you could probably get away with that if you're careful. Now, she went from the diving board down to the water, so the delta Y is negative. Same thing as what we talked about in the last problem. At some point, you've got to catch that error, hopefully. So we want to know what's our final speed. So it looks like we're doing the same equation we did in the last problem. This one. So VF squared is VI squared, that's 0, 2A delta Y. So 2 times A times delta Y. So you see here, if you had missed one of those, you'd be trying to take the square root of a negative number. And that is not happening in physics class. So we need the square root of 200, right? Which is about 14 meters per second. Now, when you square root something, that's plus or minus, right? So it's her final velocity is 14 meters per second, but it's in the down direction. So whether you just say down or whether you put a negative sign on that, we should recognize that that's what's going on. Now, she comes to a stop 2 meters below the surface of the water. Find the force on the swimmer by the water. So this time we're going to have to start with finding her acceleration, and then we're going to have to work back to the forces. So her acceleration, now her initial velocity is negative 14 meters per second. Her final velocity will be 0, and that's going to happen. She's still going down, so negative 2 meters. And the time, I'm going to put it in the list, but that's the thing that I don't care about. Again, same equation. VF is 0, VI negative 14 squared plus 2 times A times that. So when I square that, subtract to the other side, my acceleration is going to come out to be positive here, which makes sense because if she's going down and she's stopping, her acceleration, just like the tapping of the broom, is going to have to be the other way. So that would have to be positive. So let's see, what do I have here? 14 squared divided by 4. And it's super important to recognize that that's up, because now when we make a force diagram, you know what gravity does when you're underwater? Do you know? It doesn't do anything. It doesn't change, because it doesn't care. So the force of gravity on our diver is still 650 newtons. If you're like, yeah, man, but I feel like all light underwater, you know? Well, that's because there's buoyant forces, because you're like floating a little bit or somewhat, whatever. But gravity is still exactly the same on you. So this is the force. Oh, let's see. What do we want to say? This is the force of. I don't want to say it's a force of water on the diver from the water. I really don't want to have the same thing here and here. The force is definitely from the water. How about the force of stopping? I don't like that either, but whatever. I'm not going to bust you about that. So here, the unbalanced force, winners minus losers, the force of stopping is winning versus the force of gravity. So unbalanced force is equal to mass times acceleration. So her mass is 65. Her acceleration we just found is 49, is equal to the force of stopping. That's what we want to know, the force on the swimmer by the water. And we got it now, so 65 times 49 plus 650 is about 3,835 newtons. Which, if you compare that to like how much gravity she usually feels, that's a lot. All right, last problem from this assignment. During a head-on collision, if you tried these problems on your own, like this one, for example, and it didn't go so well, which is fine. I mean, the first time you try these, they're kind of hard. That's fine. But right now, before you watch me do this, you should try to do this one yourself again, not watch me do it. You listening? All right. During head-on collision, a passenger in the front seat of a car accelerates from 13 meters per second to rest, so final velocity 0, in this much time. So I've got my VI, my VF, and my T. So I'm just going to jump right in here because I got a good feeling about this. So VI, VF, T. Since I have these three, can't I just use... Sorry, I'm getting ahead of myself. So this is the VF. There's delta X. Not going to use that. VF is equal to AT plus VI. That kinematics equation, we haven't used that one yet. So I have final velocity 0 is equal to acceleration times time plus initial velocity. So the acceleration is, when I move this over and then divide, I'm going to get 133 negative. Does the negative sign make sense there? Yes, because if the car is going forward, then the acceleration that's stopping them is the other way, right? Ball's moving forward, tap, 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 the other way to slow it down. So that makes sense. All right, so how about the calculate? Oh, I did that, didn't I? That's what I was supposed to do first. Look at that, I did it first. The driver of the car holds out his arm to keep the 25-kilogram child who's not wearing a seatbelt. 25-kilogram child, that kid should be in a car seat still, or like on a booster seat or something, from smashing into the dashboard. Oh, to the dashboard, and they shouldn't be in the front seat. Oh my goodness, who are these reckless people? How much force must he exert on the child? Did any of your parents ever do this? Like my mom used to do this to me when I was a kid. The karate chop into the chest when she had to like brake suddenly. So let's see. The driver of the car holds out arms. So 25-kilogram child. So if you've got unbalanced force is equal to mass times acceleration, if the car is going this way, and then therefore the kid is going that way, then I'd have the force of gravity on the kid from the entire Earth is 250 newtons, 25 times 10. The normal force on the kid from the seat is going to be 250 newtons, but the unbalanced force is going to be this force from the driver's arm. So this is a force of, I guess we could call that a force of push on the kid from the arm. So that's the unbalanced force. And it's in the negative direction, right? If the car is going this way and the kid's going this way, that's the other way. Same deal as before. If you forget that negative sign, you should be able to recover from that mistake. But you got to think about what the numbers mean that you're pushing around. Unbalanced force is equal to mass times acceleration. That's equal to negative. So push, so 25 times 133. Oh, that's about, that force of push has to be equal to about 3,300 newtons. Oh, what's the weight of the child? Well, the weight and gravitational force are the same thing, so 250 newtons. Okay, so convert the forces in parts B and C from newtons to pounds. So to get from newtons to pounds, you have to divide, if 1 pound is 4.45 newtons, you have to divide these by 4.45. You can set up like a little conversion. So the weight of the kid, which is 250 newtons, if you wanted to convert that, this is a conversion factor, so that means 1 pound can be on the top, which is the same as 4.45 newtons on the bottom. So how many pounds does this kid weigh? 250 divided by 4.45 is about 56-pound kid. Definitely should still be booster seat in the back seat. And this force of push we want to convert that. 1 pound is 4.45 newtons. 3330 divided by. That is about 750 pounds. So, you think the driver can stop the kid? Nope. You ever lifted 750 pounds? I mean, if you think about what this move is, it would be like lifting, it would be like kind of bending over and lifting 750 pounds by lifting your arm up, like kind of up backwards. You think you can lift 750 pounds that way? Nope. That is not a good method of child restraint, the karate chop method. Go tell my mom about that.